integrated master student at NISSCR in India. And we mostly worked in homological algebra and category theory. With that, I leave it up to him to present whatever we did this summer.
Yeah, thanks. Thanks to the organizer for organizing such a wonderful program. And thanks, Pranit, for the wonderful discussions and fun discussions in the meetings. So I'll be talking about homology via homotopy colimits. Basically, we'll be covering these topics, data type categories, homotopy colimits, infinity categories, and Eilenberg MacLane spaces. So the flow of the talk will be like this. First, we'll talk about Abelian categories, quotient complexes, and cohomology. So these are the basic definition of category theory. So an additive category is such category where the home set is an Abelian group and the composition is bilinear, and it has a finite biproduct. In Abelian category, the main thing is that the first isomorphism theorem holds, and so in Abelian category we can define quotient complexes like this. So we have objects in Abelian category, CNs, and maps like D, such that the composition of two consecutive maps is 0. So this is called a quotient complex. So it's called co-chain because the index is rising. So chain complexes index will diminish. So for a quotient complex, we can define homology like the kernel of dn minus dn modulo the image of dn minus 1. So image will be contained in the kernel because d square is equal to 0. So we can get the homology like this. So the homology kind of measures how much the sequence is from exactness. So if the homology is 0, you can say the sequence is exact. So we can define the category of chain complexes in A like this. So the morphisms between two chains are some index inside F. So some map F such that F and C into Dn are maps such that this diagram commutes. So if we have a map like this, we'll have a map in homology also. So from agent C to agent D, we'll have a map of agent F. We can define additive functor. So a functor between additive categories is called additive functor if the it satisfies that group homomorphism law. So equivalently, that fx plus fy should be f of x plus y. So it's kind of good with relation to the plus notion. So additive functor is called left exact if it satisfies the exactness from left side, right exact if it satisfies exactness from right side. It is called exact if it satisfies both left and right exactness. So with this, we can go to the derived notion of the derived categories. So first, we'll discuss what is a quasi-isomorphism. So if I have a chain map from A to B, two chain complexes, it's called a quasi-isomorphism if the induced map in homology is also isomorphic. So agent A to agent B are isomorphic for all n. So one example of this type of isomorphism will be quasi-isomorphism will be if we have a projective resolution of a module, we can get two chain complexes, one for of the projective module and one for the m at the 0th place and rest of them 0. So the left side is exact, so everywhere we'll get 0, 0, 0, and at 0th place we'll get homology m, and the right side is also exact, also 0 thing, so it will be 0. So this is a quasi-isomorphism. So let's define what is called a homotopy. So if I have a map from A to B, like chain complexes A to B, if you have some diagonal maps like SNs, like from AN to BN plus BN minus 1, AN plus 1 to BN like this, if this if this type of maps exist such that f is equal to SD plus DS, then we'll say that our f is homotopic to chain homotopic to 0. So why this notion is important? If f is chain homotopic to 0, the map in homology will give us a 0 map. So if two maps are chain homotopy, is if f is chain homotopy to G, or we can say f minus G is homotopy to 0, then agent of f will be equal to agent of G. So two chain homotopic maps gives us the same map in homology. So the homotopy relation is kind of like ideal like relation. So f is chain homotopy to 0, G is chain homotopy to 0, so f plus G will also be chain homotopy to 0. So by this, we can define what is called the homotopy category, Ka. So A is an Abelian category. The objects are same of like complex of in A, but the morphism will be morphism in form A modulo homotopy to 0. So if f is homotopy to 0, the map will be basically 0 map. Now, we can localize this category. What do you mean by localization? So if I have a quasi isomorphism, I can kind of invert it and it will give us an isomorphism. So DA, the derived category, we can get it by localizing quasi isomorphism on K. So what is the universal property to define such things? If we have any functor from K to D such that quasi isomorphism maps to isomorphism, this will uniquely factor through the DA. So basically what is happening that in DA, our quasi isomorphisms are exactly isomorphism. So let us define a well-known thing called cone of a map. If f is a map from A to B, we can define cone of f like A1 plus B. What is A1? A1 is A shifted by 1 to the left. So the ith component of cone f will be A of I plus 1 plus Bi. And the differential will be given by this type of matrix thing. We can check easily that the differential square is 0. So it is really a chain complex. And this cone gives us a notion of this cone gives us a notion of acyclicness or so if we have so the cone is defined such like that this short exigent sequence is followed that from B to cone F to A1, and from this short exigent sequence we get a long exigent sequence in cone. So if our cone F is acyclic, means if the cone F is exact sequence, so our total HIs will be 0. So we'll get isomorphisms in HI A to HI B. So everywhere we'll get an isomorphism. So our F will be quasi isomorphic. So this gives us a if and only condition. Now a notion. So in classical homology theory, you have notion of projective resolution or injective resolution. Similarly, here also we can have the equivalence of these two categories. So K minus P is bounded above category of projectives. This is completely equivalent to D minus A, the bounded above category of P. Or dually, the dual statements also hold. So these isomorphisms gives us resolutions of a complex, basically bounded above or bounded below complex. Now we can talk about the main thing of the talk, that C star functor. We have a functor from top or topology or CW complexes to D of AB. The functor basically gives us a set, say, topological space X to its C star X Z. In D of AB, the AB is Abelian group. So the derived category of Abelian group, the functor is really the homology functor. The C star XZ is isomorphic to homology if we have good enough maps. And we can also see that the cohomology is basically dual of the homology. So here Z in the second line is ZK is Z at the kth space. So the kth cohomology will be same as the Ck of Xz, which is isomorphic to Hom of C star of a lower star Xz to Zk. So homology and cohomology is kind of dual notion in our derived category, and our C star exactly gives us the homology thing. So this kind of redefines our usual topological algebraic topological homology into this thing. And our C star preserves Hocolim. So we'll discuss what is Hocolim now. Hocolim or homotopy colimits are notion in kind of infinity category theory. So hard to define in one category way. So if a category witnesses the notion of a homotopy equivalence, so the homotopy colimit will be the notion of the colimit where the commutativity of the diagram is substituted with the homotopy equivalence, and this data comes with its own data of homotopy. So we can kind of calculate one Hocolim in a top category. Maybe here I have written the answer anyways, but the push out of this diagram x to y and x to star, this if I have a map from x to y f, this push out of this diagram in homotopy colimit will be the cone of f, from the mapping cone of f, our usual topological mapping cone. What is the map? So why this happens? Because if I have some another map Z such that our alpha prime f is basically null homotopic. It's null homotopic because it has to be homotopic to x2 star to Z. So it maps x to a point in Z. So if it is in the exact null open homotopic, it will be exactly factored through the cone of it. So this gives us this cone is a homotopy push out of this diagram, homotopy column. Yeah, and our sister maps star or a point to exactly the Z0 complex. You know that the homology of a single point is concentrated around the 0 Z, and we can see that CW complexes are completely generated by this one single point and the cone of this. One example, we can see that if we want to attach a disk, we'll just have to map S1 to X by an alpha, and push out of this diagram will be attaching a disk on X. So we defined cone for derived category also. So the name was not clear that why we say this is a cone. This is because in homotopy category, the homotopy colimit is exactly the cone of f. So alpha f is exactly zero map, homotopic to zero map, and any zero map factors to this. And similarly, the cylinder of two maps f and g is same as the cone of f plus minus g. You can easily check this. This happens because f plus minus g is homotopic to 0, means f and g will be kind of homotopic to each other. So the functor top to dab. So d minus ab because it's we can basically bound it from below. But the question arises that this functor, does it preserve cone or not? So if I have a diagram like this, x to y to x to y and x to a point, the cone of this diagram will be CA. And if you apply C star everywhere, so is C star of CF cone of this diagram? The answer is surprisingly yes, because by Meyer-Vitteris, we can apply Meyer-Vitteris to this and get this thing. And so this functor, this nice functor preserves cones, co-products, so it preserves all the colimits. So we have a functor that preserves colimits. Now we'll talk a little bit about infinity categories and raise this functor to infinity categories. such that we can apply adjoint functor theorem on them. So what are infinity categories? Infinity category is some kind of simplicial set with some nice property. So the zero simplexes will be objects, one simplex will be one morphism, and two simplexes, two morphisms, and all. And map. So in the home set of this infinity categories is replaced by mapping space of AP. So we are not going to the total definition of what is a mapping space. It's a CW complex of like such thing, but home set is replaced by mapping space, and equality and isomorphisms are replaced by homotopy equivalence. So we see that colimits in infinity category are precisely the Hope-limits. So everywhere we're calculating Hope-limits because we need colimits in infinity category. So the functor top to DAB and these two categories and this functor can be raised to infinity categories. And we have a adjoint functor theorem for nice enough infinity categories that if I have a colimit preservable functor, that then this F functor has a right adjoint. So by this theorem, we saw that our C star there preserved colimits. So we will have a right adjoint of this called K. And by this adjoint pair, we'll have this adjoint thing, map in DAB, Cx to Mn. So Mn is M is an Abelian group at nth place. So the chain complex is concentrated on the nth place. So Mn, and this is isomorphic to mapping topology from X to Kn. So this is just the adjoint pair by the adjoint pair. So one category level, we have Hom Cx to Mn, so which gives us exactly agent homo. So it was the dual homology was the dual of homology. So it exactly gives agent Xm. So cohomology of Xm, and this is basically our the great Brown representability theorem that the homology is representable. It's representable by this functor X to Kn. If I put X to be Sk, the K sphere, we can get this pi K of this Kmn to be exactly as agent of Skn. So if our n is equal to K, I can get that this is equal to exactly M, and otherwise it is 0. It's 0 everywhere. So pi n of this Kmn will be M, otherwise it is 0. So you get a space Kmn like this, such that only the nth homotopy is one group, Abelian group, and the rest of the homotopy groups are 0. So these details are not for pointed space. The same details can be worked out for pointed spaces also. So instead of having top here, we'll replace it by pointed spaces. So the same things work out, and I will define KGNs as the Eilenberg MacLane space with nth homotopy group G. So this is the same calculation as the before thing. I'm putting instead of X, we put X and X naught. So SK is pointed at X naught, and the SKs are pointed at a star or a point. So this gives us the Eilenberg MacLane space with n homotopy group G. So these are the references. Stop. So yeah, thank you. And yeah, if you have any questions, please ask.